Hello and welcome to my dissertation video. This is Michael Perez and I'm working with Stefan Poslad as my supervisor. This video will go over the different aspects mentioned in the MSc handbook. These are things like the areas I've worked on. I'll talk a little bit about the problem statement, description of the different methods I used. So, the problem statement that I hope my dissertation had covered is that stemming from a World Health Organization article about the number of deaths annually. In fact, actually, 684,000 deaths occur annually just on falls, and with a majority of those being from individuals over the age of 60 years old. So it is quite evident that the elderly are the individuals that are at the highest risk, and the majority of the time, these elderly people are in care homes or they're isolated. The idea here is that I would like to create some sort of alert system available to automatically detect when a fall occurs and potentially stop deaths from occurring because they get the support they need in the time. Here we present my solution. It deals with a individual that's fall, and their fall will be able to be picked up by a microcontroller, either an Arduino or Pico. A machine learning classifier is running on this microcontroller, and then it's sent via serial connection to a web platform. I'm going to now discuss the main topics that I worked on, what I needed to understand before I could go further in this project. This included microcontrollers, audio classification, and TinyML, in which case TinyML is the subset of machine learning dealing with running on controllers, tiny IoT device. So for microcontrollers, I worked with two of them, Arduino Nano 33BLE and also the Raspberry Pi Pico 2. And in our table on our dissertation, we use these two, which have varying levels of RAM and ROM, as well as different number of cores, but also some don't really support floating point arithmetic. And this becomes troublesome later on. Audio classification was a big one for me because there's a lot of terminology, there's a lot to do with taking an audio sample and what is a sample rate in this case, what is a frequency, what is a FFT magnitude, windowing, spectral leakage. And so there was quite a lot of work in terms of understanding audio. How, well then, if I know the different aspects of audio, how do I translate a microphone signal to some feature set that I really like? TinyML, we had a few stages. This included audio processing, model creation, model training, hypertuning, model testing, and then deployment. First step was the audio pre-processing. This included taking the continuous audio and splitting them, sorting them out, labeling them, etc. We then went on to model creation. So here is the CNN model, which uses the MFE. Here's a snippet of the code for running these, and this is the RNN. This is another different type of model which utilizes more temporal information. I use a conjunction of both these models, which I explained in the paper as well. And then during the actual learning, I used my local GPU and also a platform called Edge Impulse, which is specifically for training edge device. I then went into, say, tuning the model quite a lot. Actually, this ran 15,000 times. I let it run continuously. And then what happens is when we have this model, we convert it into a TensorFlow Lite model. This kind of compresses it and it uses some technology called flat buffers from Google. And so once you have this tiny TensorFlow Lite model, you can then flash this onto, say, an Arduino. What were the other solutions in literature? They included wearable sensors, vision-based sensors, and ambient-based sensors. Wearable devices included accelerometers, gyroscopes, and they required the user to have a wristband on. But say if you had a watch, maybe you want something to be as passive and not actively looking at it. Vision has privacy concerns. You don't want to be recording, say, regardless if it's infrared or it's an RGB camera, because, or even worse, a depth sense camera, because then it's invasive, and the aim here is privacy oriented, and it runs local. And then there's ambient based sensors. So this includes placing, say, RFID sensors, pressure sensors. However, these are quite expensive and is not really feasible in terms of reproducing them. My dissertation aims to provide an inexpensive solution, and they all fail in terms of the data set, which uh, I mean, it is a valid point that uh, obtaining genuine data for fools is quite difficult in terms of you can't get an elderly person to fall because it may risk them and it may be unethical. In my case, I used padded pillows and I fell on that. Now I'm going to demonstrate the practical. And as you can see, the model has detected a fall a few seconds ago with 3 different inferences points where it detects a fall for 3 separate occasions. The additions of this paper is that there is a real-time focus. It runs in real time, and that took quite a lot of tinkering, engineering. Privacy and its design is that it runs locally. There is no communication with the cloud or any external parties. Is increased portability. You can place this anywhere in the room. It can be passive, it can be out of mind. It's a low cost solution. In fact, it can cost you roughly £30 max, I would say, £25. So this went through an iterative process. I initially started with electronics, understanding interrupts, how to get the pins working, how does electronics from theory to practical work, and then I got into voice controlled LED projects. So this was saying different colors, and also I can say 1, 2, 3, which will blink the current state as many times as I said. This also introduced the challenges of active listening. In this case, it's really difficult to have adequate time to process, but then also listen without overfilling different buffers. And I'm using something called a double buffer mechanism. So recording started where I collected data through pressing a button. This was a custom script. The LED will turn red, and once done, white would mean it's saving, and it would save this in a Google Drive folder. Next, I thought, well, really, it's taken a long time, so I then deployed 4 different microphones all over the place. So when I fell, I just pressed one button and they all start recording. And I experimented with different parameters so that each microphone has a different configuration so it can generalize well. Little did I know that kind of failed, and I had to make another additional data set on a different microphone so it can generalize better. That's what I was saying. It didn't generalize well. Actually, even touching the table or walking triggered the alert. It turned green with high confidence. And so that required me to retrain the model. Then it worked. Here is a LSTM model, which is using a Pico device, has much more capacity to do more. So it was able to run such a model. It required using some libraries because it did not have any float operation support. So I had to convert numbers to ints. I had a lot of optimization, so pre-computed matrices. There was a trade-off between storage and processing. The idea here was that it needed active listening, and this is a really big problem. And the idea is that I had 2 buffers, and the buffers are buffer A and B, and it records for 1.5 and it has to process within 1 second to be able to maintain these buffers. What happened was that I was not able to process within the 950 milliseconds to be able to achieve active listening, and so it can only listen and then process. I think the idea here would be that I could possibly do it if I knew more about how to parallelize the program. So that includes using threads and DMA, so direct memory access. There's a lot of things very low level. Problems faced in the project. In order to have quite an accurate model, you needed quite a lot of feature points in the audio signal, and this increased processing time. And when there was an increase in processing time, the ability to actively listen diminishes. So you kind of need to experiment between the number of frequencies you would like to capture, how that would translate to processing time. So to conclude the project, I ran 2 different models, a CNN on the Arduino BLE and an RNN model on the Pico 2. The CNN showed quite good results, as shown by the CNN confusion matrix, roughly a F1 score of 94, with manageable latency and memory size usage. However, due to the complexity of the problem, so things such as steps, something similar to the sound, the CNN could not capture this difference, and so a more temporal oriented machine learning solution was needed. That was the RNN, which I ran on the Pico. And because the Pico had an increased capacity, it did allow for a higher accuracy. In fact, the test accuracy is 95 compared to 93. I mean, this small difference did actually make a difference in practice. However, it did require a lot of digital signal processing and infeasible to actually run on the device. I had to run this on my desktop. I can conclude that the project itself provides researchers exploring this field a methodology. What are the possible trade-offs? Specifically, what are the risks involved, such as the need to generalize well by using two microphones? I'd like to say thank you for listening to my video, and thank you for my supervisor, Stefan Poslad.